Well, hi there, boys and girls. Today we're going to talk about Euler's method, which is a method of approximating the solution to a differential equation if we cannot find the actual general solution or particular solution. So this is an approximation method that we use in BC calculus or in calculus if we cannot actually find the original solution. Now, I want to show you the difference between Euler's method and the regular old tangent line approximation. The tangent line approximation at a specific point will match the slope at a point and it will match the graph at a point, but after that it's probably not going to match the curve. Here's an example of a tangent line, and you can see this tangent line is pretty close to this curve, but once we start getting further and further away, the actual y value right here is much taller or further away than the y value of our particular solution. And so this delta y here is fairly large, and it's not really acceptable as we move further and further away from this initial point. I also want you to know something. This is very important. Our particular solution is concave down. And if your solution is concave down, the tangent line will be above the curve. And that is why we get an over approximation if we use the tangent line. This is an over approximation for all these values as long as our solution is above the curve. Okay, now let's take a look at Euler's method. Euler's method says use the tangent line, but just for a little bit. Just for a little bit here. And so I'm going to call that, we're going to erase that because that's actually pretty horrible. We're going to try that again. Use the tangent line for just a little bit. Oh, I know what I can do. We're going to come up here and do this. Sorry about the little random mark there. Use the tangent line, but don't let it go forever. So this tangent line had the slope at a0, but we're going to call this a step size of delta x. Then Euler's method says stop right there and then do a new tangent line, except I want you to follow the slope at this new point. And so we follow a different slope at this new point, and we change our slope, and what we end up doing is we stay closer to the curve. The original tangent line would have kept going like this. But if we stop at these delta x's or these step sizes, I'm going to write that, these baby steps, we stop and reevaluate our slope, then what we're going to do is we stay closer and closer to the actual solution. I'm going to add one more thing here. This graph, this particular solution, this is a concave up graph. Where did our tangent line approximation fall? Well, it fell below the curve. And that is always going to be true. Euler's method, which is baby step tangent lines, will be below the curve or an under approximation. Get some specific examples here. Well, let's actually look at the general procedure. We know from our old tangent line equation that f of a plus f prime of a times x minus a, this is equal to our tangent line equation. This is our t of x. That's a t over there, by the way. That's our t of x. Let's do that. All right, what we're going to do is we're going to say that our new y, or f of b, is equal to f of a, that's our old y, plus the slope, this is slope, f prime, and notice this f prime is at the old y, times, and we're just going to call x minus a our delta x, or our step size. And this is how, this is still a tangent line approximation, except we're going to have these little baby steps, and the step size is going to be those baby steps. Alright, so here we go. Let's take a look at a differential equation we saw yesterday. dy dx equals x plus y, and we drew this slope field. And let's say we had a particular solution, or a initial condition that y of 0 equals 1. So we're somewhere like right here. And we want to approximate, using Euler's method, y of 0.2. In other words, we want to go out here to 0.2 and see where we're at. Now, we can tell from this slope field that our graph is concave up. This graph is definitely concave up through this point. So will our approximation be an under approximation or an over approximation? So that's just a question to think about. Now, the tangent line would keep going all the way to 0.2, but we want to do a baby step. and you are typically given a step size, and let's do a step size of 0.1. So what I'm going to do is draw a little table. My table is going to look like this. We're going to start at 0, 1. Then we're going to get to 0.1 comma new y. I don't know what that is. And then we're going to finally end up at 0.2 comma. This is our approximation once we do our Euler's method. We're going to stop at 0.2 comma something. This means we need to do 2 baby step tangent lines to get to 0.2 to get to our approximation. So let's see how that looks. So we know that our old y plus the slope times our step size is my approximation to get, I keep running out of room here, let me see if I can do that, to get our new y. So let's see what that looks like. So I'm going to say y at 0.1, which is our new y, we're going to go to this point first, is equal to the old y. Now what was our old y? Get this back over here. Our old y was 1. That was like the beginning. So it's 1 plus, now we have to calculate the slope. The slope comes from dy dx, and that was given to me up here as x plus y. So I'm going to write down that dy dx at this point, which is x plus y, equals 0 plus 1, x plus y, which is equal to 1. So that's the slope that I'm going to use there, times the step size. The step size is 0.1. So this is 1 plus 0.1, which is 1.1. And that is my new y. I'll put it right there. So what we've done is we've gone just a step size of 0.1 with a little baby tangent line, and we are up just a little bit. Of course we're up because this was concave up. Function was increasing, but this is still below the curve. What we're going to do now is we're going to do a tangent line from here. We are forgetting about this for now. We're now going to do a tangent line from here. This is my new x and this is my new y. So to get my next approximation, which is where I'm stopping, I'm going to say that y of 0.2 is equal to, I actually should use some approximations here instead of equal to. That will make me feel better. Y of 0.2 is approximately equal to the old y. Now my new old y is 1.1. I'm going from this point. 1.1 plus. Now I have to do the slope, and the slope at this new point. I've forgotten about that old point here. And remember, our slope is dy dx equals x plus y. So dy dx equals x plus y, which is 1.2. That's my new slope. So I'm going to do 1.2 times my step size. So I've got 1.1 plus 1.2 times 0.1. Alright, so what is 1.2 times 0.1? Well, don't we just move this decimal over one place if we have a 0.1 here? We're going to move this over. So this is going to be 1.1 plus 0.12. That just makes sense. Multiplying by 1/10 just moves it over 1, which gives me an answer of 1.22. That is my approximation. That is the answer to Euler's method, 1.22. And I'm going to say that y of 0.2 is approximately equal to 1.22. And on top of that, I know this is an under approximation because my original curve, I could tell from my slope field, f of x is concave up. I can tell that from my slope field looking at this again up here. You can tell through here this is all concave up. So that's my approximation. That's how you use Euler's method. Let's do one more example so you can see this again. Consider a function whose slope is given by dy dx equals 2 times x times y with an initial condition f of 1 equals 1. That's initial point 1 comma 1. Use Euler's method with the step size of 0.1 to approximate f of 1.3. So I'm going to have my little table here. We're starting at 1 comma 1. We're going to go to 1.1 comma something. Then we're going to go to 1.2. 2 comma something, and finally we're going to go to, that's supposed to be a point. It's really early in the morning. I'm sorry about this. Well, 8:36. I don't know if that's really early or not, but then we're going to go to 1.3 comma something, and that right there, once we get there, that's going to be our approximation. Now I'm going to get you started here, and I'm going to see when you walk into class tomorrow if you can tell me what that approximation is. Which is when you walk in, just say, Mr. G, it should be this. But I'm going to get you started. So we're going to say that y of, well, we're using f here, so I'll use f. F of 1.1 is approximately equal to, we use the old y, here's your old y, plus your slope. Now the slope here, I have to look at my slope field, or my differential equation. I haven't drawn the slope field yet. The differential equation says 2 times x times y. So that's 2 times x times y times my step size. My step size is 0.1. So let's see if we can do that. This equals 1 plus 2 times 1 times 1 is 2, times 0.1 is 0.2, which is 1.2. That's what I think f of 1.1 is. Now this is your new point. You are going to forget about this now. So when you do f of 1.2 is approximately equal to, you're going to use this. This is now your old y, plus you use the slope, and here's how you find the slope. 2 times x times y at this point. So it will be 2 times x times y. And then times your step size. So I want you to do that. That's your new approximation here. Go through one more iteration, and then tomorrow in class tell me what you got there and see if we agree. So that's the basics behind Euler's method, baby tangent lines, and I will see you guys tomorrow.